Okay, so today we continue with the Fourier series. Remember, the last example we did last time was the function x. We found its Fourier series. This was the Fourier series in the final form. Then we tried to explain the geometric meaning of the Fourier series, that the partial sums start getting closer and closer to the original function, as this graph shows. Now we continue with another example, and in this example I'm going to take the same function x, but this time I want to do it as a periodic function. Just to remind you what we did in last time, we took the function x only on the interval negative pi to pi. Now let's see what happens if this function is extended periodically. So we continue. So let f of x equal x. Now I want this function x not to be not this function only, but I want it to be extended periodically. When we say extended periodically, that means you copy paste that part, so you have these infinitely many lines segments. So how do we do this definition? So what is the function? So we all agree that it's x between negative pi and pi, but after that it's extended periodically, and it is clear for us, I think it's clear that the length of the period is 2 pi. So I want this function to be extended periodically to have period 2 pi, which means f of x plus 2 pi must be equal to f of x. So these two equations together, they are presented by this graph. Okay, so this is the function. Okay, so now if we compute, because we already did the computations for x, so if we find the Fourier series, it is what we found earlier. So it is 2 times the sum from 1 to infinity negative 1 to the n plus 1 over n sine nx. Okay, so this is the Fourier series, and that's it. This is the Fourier series of this new function, and this is the Fourier series. It's the same series exactly. For the function x defined only on the interval negative pi to pi. Okay, and this is, I think this makes a lot of sense, because if you look at the Fourier series, it is composed of sinusoidal functions, we call these. So this function is periodic of period 2 pi. So it makes a lot of sense that when you draw this function on the interval negative pi to pi, you get something, and then this thing must be repeated periodically. So now what happens if we draw the partial sums of this function? The partial sums will be getting closer and closer to this red graph, the line segments. So basically, after drawing many of the partial sums, you will find that the curve, the partial sum, is getting closer and closer to your curve. Now this part we did it last time. Now what happens when you jump from this red part to this red part? It's very nice that the Fourier series jumps quickly. It moves very quickly to cover the other part. This is exactly what happens when you find the Fourier series of this, let's say, piecewise function. So this purple part repeats periodically. The red part is periodic, but the difference is, the purple part is a continuous periodic function. The red part is not continuous. So basically you are approximating a non-continuous function using continuous functions. I'm not going to say very easy functions. The sine functions are not that easy, but at least you have the ability to approximate discontinuous functions using continuous functions, and those continuous functions behave in a very strange way, that they jump. You see, it's a very quick jump to cover this discontinuity. This is a very nice property of the Fourier series. Now to revise all these things together, so we start a new example. So if we take the function, now I'm going to take the function x square, but again, not the x square on the real line, but the periodic function x square. So again, I'm taking the interval negative pi to pi as my basic interval. And now you may ask what happens if we change this interval. I will show you later. But basically, the basic period is from negative pi to pi. Once we understand this concept, everything follows from this. I will show you how to deduce any period from the period 2 pi. Okay, so if you take this function, then you extend it periodically. So again, the role of this equation here is just to say this. So you're taking the function from negative pi to pi as x squared. So this is x squared, the function that we all know. But after that, you extend it periodically. So in this case, if you agree, this periodic function is continuous. When you extend it periodically, it is continuous. Okay? But for example, it is not differentiable at these points. These points, we call these points cusps. At these points, the function is not differentiable. So now, for this function, let's find the Fourier series. Okay, this is a standard procedure. So to find the Fourier series, we need to find A node, we need to find an and bn. What was the A node formula? It's 1 over 2 pi, integral from negative pi to pi. Let me erase this so you don't avoid it with a negative sign. F of x dx. This is an easy integral. It's the integral from negative pi to pi, x squared dx. Now I'm going to say, because we need this idea later, okay, this is an easy one, but the idea is needed later, so I want to introduce it from now. The x squared is a periodic, is an even function. So when you're dealing with an even function and you're integrating it from negative pi to pi, you can replace the integral by double the integral from 0 to pi. And now this is 1 over pi. The integral of x squared is x cubed over 3 from 0 to pi. This is what you get. So basically, you're getting, in the end, pi squared over 3. So this is the A node. So A node is pi squared over 3. Once we find a node, we move to an. We proceed to find an, which is 1 over pi, the integral from negative pi to pi, f of x cosine nx dx. Now again, in this example, between negative pi and pi, the function is x squared. Now clearly, the x squared is an even function. The cosine is an even function. When you multiply two even functions, you get an even function. And if the integrand is even again, you can replace the integral. Instead of having it from negative pi to pi, you can replace it by double the integral from 0 to pi. And now, of course, for this integral, you have to do it by parts. So let's do it by parts. So you do it aside, anywhere aside. So for example, if we do it here, if we can do it in this little space here. So this is the u, this is the dv, the u is x squared, the dv is cosine and x. We differentiate, we integrate on the other side. Then you differentiate again, you integrate again, but this time you get a negative sign. You can differentiate again, integrate again. Then, of course, we know what to do next. We multiply diagonals. The last one is horizontal multiplication. The signs are alternating. The last one comes with a negative, with an integral sign. So this is the integral. Now we just copy what we've written here to the integral. So this integral becomes 2 over pi times something, and the limits are from 0 to pi. Now, what is inside these brackets? We take it from here, from the integral. So we need to multiply x squared with sine, 2x with cosine, 2 with sine. Now, I'm not going to write the sine terms, because if you agree, if you write the sign terms, then you need to substitute the pi and the 0. These are the limits of the integral. But when you substitute the pi or the 0 in the sign, you get 0. So there is no need to substitute them. If you don't like it, do it, write it, then you get 0. So basically the only term that I want to write is the second term, which is 2x cosine n x over n squared. Okay? So this becomes, now we substitute the pi minus we substitute the 0. Because of the x, when you substitute the 0, you get 0. So what's left is 4 over pi n squared times pi cosine and pi. If you like, let's write minus 0 just to make sure that you see it. Minus 0 when you substitute the 0. So now the pi gets cancelled. Then you're left with 4 times cosine and pi over n squared. The pi again. This pi is cancelled here. So what's left up is just cosine and pi, which is negative 1 to the n. So this is an. This is an. Once you find an, so remember, we wanted to find the Fourier series. This is a node. This is an. After that, you just need to find the bn. The bn is the integral from negative pi to pi, f of x sine n x dx. Now, things are a little easier because the x squared is even, the sign is odd. When you multiply an odd function with an even function, you get an odd function. And of course, when you integrate an odd function from negative pi to pi, what you get is exactly 0. So what this tells us is that all the bn's are zeros, and now we are ready to write our Fourier series. So our conclusion for the function x squared from negative pi to pi extended periodically for this function, what is the Fourier series? To remind you, it's a node plus the sum from 1 to infinity. What's the summand? It's an cosine nx plus bn sine n x, which is in our example a node. This is it. It's pi squared over 3 plus the bn's in this example are all zeros, so this is basically 0. So plus, what is the an? The an is 4. We can take the 4 out, times minus 1 to the n over n squared times cosine nx. So this is, and this is 3. Just to avoid anything. So this is the Fourier series of our function. This is the Fourier series of our function. Again, just to make sure we got this idea, what is the geometric meaning of the Fourier series? Again, it means if you draw the function, which is x squared from negative pi to pi, then if you extend it periodically, so the red curve is the original function. Okay? So this is f of x. Then if you start drawing the partial sums of the Fourier series, in this example, what are the partial sums? Just to make sure we get everything. The partial sums of the Fourier series, the first term, which we call S1, is pi squared over 3. Then S2 is, you take the first term plus the second term. Now what's the second term? The sum is from 1 to infinity. So you substitute 1, that gives you a negative sign because of the negative 1 to the n. So this is negative 4 cosine 1x, of course, over n squared, which is 1. Then what is S3? It's pi squared over 3 minus 4 cosine x. Then when you substitute the 2 into the summand, you get plus, of course, 4 over 2 squared, that's 4, so they get cancelled, cosine 2x, and so on. So you keep substituting these numbers. Now, what is the pi squared over 3? Pi squared is a little bit bigger than, it's bigger than 9. So basically, pi squared over 3 is something like 3 point something, okay? 3 point something. Now, what is this number here? This number here is pi squared because the function is x squared. So basically, pi squared over 3, if you draw it, it's a straight line, but that is like this. It's almost a 3 point something, so it's a way lower than the pi square. Then what the partial sums tell us is, if you keep drawing these functions, so if you draw this function, then this, then, and so on, after some terms, and again, I encourage you to do it. We did it in a class, if you remember, using Mathematica. But if you do this, in the end, in fact, not in the very end, I mean in the end, if you draw like 20 terms, 30 terms, 100 terms, you will see that when you draw the partial sums, they will be very close from your original function. So this is the main idea of the Fourier series. Just do it and you will see how these terms gets closer and closer to the original function as you're taking more terms of the Fourier series. Okay, so these are the computations of the Fourier series. Now, before seeing more examples on how to find the Fourier series, and I'm sure at this stage it's clear that finding the Fourier series is not a big deal. I mean, it's just a matter of computing some integrals, so it's not that much. In the worst case scenario, you can use any software, even if the integrals are very hard, even if they're not computable, by the way, because some integrals, we can't compute some integrals. In that case, we can use numerical techniques, and these numerical techniques are built in any software like MATLAB, Mathematica. Even your scientific calculator can compute these integrals numerically using some approximations. But again, in the end, you just need to compute these integrals to find the Fourier series. It's not that much. Now, I want to talk a little about this question. So here we have a question. So given a periodic function f of x, say, do we have Fourier series of the function necessarily equal to the function? This is a very important question. So you're computing the Fourier series, and now we're asking what's the relation? This is the question basically. What's the relation between the Fourier series and the function? Now, what we are explaining, whether in this example or the one before, is that yes, what we're saying, if you draw the two functions, then the Fourier series is getting closer and closer. And if you are able to reach infinity, which we can't do, but if you're able to reach infinity, you will see that the Fourier series is identical with the original function. However, this is not always the case, and this is not always the case. We've seen this before with the x. We can see how the Fourier series managed to jump from this point to this point. So at this point at pi, what's the value of the Fourier series and what's the value of the function? We will see that the Fourier series is not necessarily equal to the function. However, this question is not so easy to answer. This took the effort of many mathematicians with many special cases, with a lot of mathematical analysis to answer. For the purpose of this course, I will be just interested in one simple case. So let me here write like a partial answer for this question. Yes, we're not answering this question completely, because the complete answer needs a lot of analysis, which is usually done in even not a bachelor course in mathematics, usually in graduate courses. So for engineers, this is of course not a big deal. What's important for engineers is that when you take the Fourier series of the function, we want it to be a good approximation for the function. So the functions that we usually deal with, they satisfy a certain thing. What is that thing? So if f is in the simplest form, if f is piecewise smooth, then the Fourier series of the function at a point x is f of x, it is f of x plus f of x minus over 2. Now, what do we mean? What do we mean by f of x plus? We mean if you take the limit as, for example, t approaches x from right, f of x, and what do we mean by f of x from left? We mean the limit as t approaches x from left, f of t, sorry, f of t, f of t. So what we mean is this. For example, if you draw, I want to draw the function x, because this is like a good example to explain. So the x is this function here as a periodic function. We're dealing, remember, with periodic functions. So even when we say the function x, we mean the periodic function x. Now, if you look at the pi, first of all, what do we mean by piecewise smooth? Piecewise smooth means this function is composed of different pieces. In this example, it's composed of different line segments. Each line segment is a linear equation, and we know that any linear equation is differentiable, is continuous. So this is what we mean by a smooth function. So this function is composed of piecewise functions, smooth ones. So it satisfies this assumption. Then the conclusion is that the Fourier series is equal to the limit from left plus the limit from right over 2 at any point. For example, if your x is pi, if you are interested in pi, and you ask, what is f of pi from left? F of pi from left means if you approach pi from left, it's very clear that this is where you land, right? So, and this point is pi, and this point is negative pi here. So basically, what is f of pi from left? It is pi. And what is f of pi from right? It is negative pi. If you approach the pi from this side, in the end, you will be approaching this point, which corresponds to negative pi. So in this case, if you're substituting the pi into this equation, what you're gonna get from this part is exactly 0. This is the meaning of f of x plus f of x minus over 2. However, in this example again, if you take any other point, for example, if you take 0, for example, so if your point was 0, I think you all agree that because the function is continuous at 0, whether you approach it from left or right, you're getting the same number, which is 0. So again, you get 0. But for example, if you take pi over 2, you get pi over 2, and so on. So at this point, I think you support the following. So basically, if f is continuous at x, then what's the Fourier series? Again, by the way, that result, the result here we just mentioned, this is usually called Dirichlet. Dirichlet is a name, and Dini is a name. Dirichlet-Dini theorem or test. Okay. So what the Dirichlet-Dini result is that the Fourier series at any point is the limit from right plus the limit from left over 2. But if the function was continuous at x, we know that the limit from right is f of x and the limit from left is f of x. So basically you're getting the same value. So now if you go back to our question, this is the question. So given a periodic function, do we necessarily have that the Fourier series is equal to the function? Yes. If the function was continuous. If the function was continuous at that point, yes. Plug the point into the function or plug it into the Fourier series, you get the same answer. Then what about if the function is not continuous? There is no big deal. The difference is very minimal, that when you plug the number into the Fourier series, you don't necessarily get the same value as when you plug it into the function, but it's the average of the two limits from left and right. Let's see an example, because I think the example is the best way to explain the significance of this result. So an example. We've just seen that if f of x is x squared negative pi pi we saw that if this is my function, then the Fourier series, we just did it. It is pi squared over 3 plus 4, the sum from 1 to infinity minus 1 to the n cosine nx over n squared, right? we just did this Fourier series. Okay, so this is the Fourier series. Now we're not asking about the Fourier series, we're asking about applying the Dirichlet-Denise theorem. So how do we apply it, and how do we tell if we need to apply it? So now we saw this, fine. Now I want to compute, so evaluate for example, let's compute the sum minus 1 to the n over n square and from 1 to infinity. What do we mean by the sum negative 1 to the n over n square? We mean if you substitute the 1, you get negative 1 plus, if you substitute the 2, you get a fourth, then you get a negative 9th plus 16th and so on, right? So this is I need to remind you, this is, what is it called? This is called, or this of course it's the same thing, this is called an alternating series. Okay, just a reminder here, from calculus 2, you learned that the meaning of the alternating series is that it has the form negative 1 to the n times bn. Of course, the limits do not matter. You start from 1 to infinity, from 2 to infinity, as long as you end your sum at infinity, it's the same conclusion. So this was called an alternating series under certain conditions. So if this satisfies, to remind you, Bn is positive, Bn is decreasing, and Bn approaches 0, then the series is convergent. This is called the alternating series test. I think it's a good idea if you just quickly Google the alternating series test and just to remind yourself of these stuff. Okay, so now if you look at the series that we have, so if you look at the series from 1 to infinity, negative 1 to the n over n square, this is the same as the sum from negative 1 to infinity minus 1 to the n times 1 over n square, right? I'm writing it this way just to compare it with this form. So when you compare it to this form, the 1 over n square, this is like the Bn. And now you ask yourself, does the Bn satisfy these conditions? Yes, 1 over n square is positive, it is decreasing. And what we mean by decreasing is that when you increase the n, the quantity 1 over n square gets smaller, yes. And it approaches 0, yes, as n gets larger and larger, the 1 over n square gets smaller and smaller, so the limit is going to 0. So we know from calculus 2, so we know that the sum from 1 to infinity, negative 1 to the n over n square, we know that it's convergent from calculus 2, okay? But if you agree, we didn't learn the value of this sum. Okay, it's convergent, so we know it has a certain value. But what is that value? We don't know. But we don't know its value. I mean, from calculus 2 again. Now what we are doing in this course, in this part of the course, is that we are able to find this sum using the Fourier series. So how do we find? So this is the idea in this example. So we want to apply the Dirichlet-Denise result to find the sum. Okay, so let's go back to this result and to see how can we apply the result to find the sum. So the idea, this is the test. So the Fourier series is equal to the limit from left plus the limit from right over 2, which means if you substitute any number into the Fourier series, you get this value, okay? So now I'm giving you, by the way, I'm giving you in my example that the function you're dealing with is x squared. So I know that, so for f of x equals x squared over pi, and I don't need to write f of x plus 2 pi is equal to f of x, we know that the Fourier series, we just found it, is equal to this. Now the question is, I want to find the sum from 1 to infinity, negative 1 to the n over n squared. So the idea is, what number, this is the sum, okay, this is the sum here. What number, what is x, that gives you this value? So what number, x, can you substitute into this term to get minus 1 to the n over n squared? If you compare the two quantities, so if you compare this summand with this summand, I think it's very clear that you need to have cosine equals 1, because you have negative 1 to the n over n squared. So if the cosine is 1, that's what you want. And the cosine is equal to 1 when x is what? When x is 0, right? So if we substitute x equals 0, let's see what happens. The Fourier series, so this is the Dirichlet test, at 0 is equal to f of 0 plus f of 0 minus over 2. Now what is the Fourier series at 0? You go to the Fourier series and you replace every x you see by 0. That gives you pi squared over 3 plus 4 the sum from 1 to infinity, and when you substitute 0 into the x, this is what you get. Equals what? F of 0 plus f of 0 minus over 2. This is my function, the x squared. This is it. So if you look at 0, this is the 0 here. If you approach it from right or from left, I think we all agree that we get 0 because the function is continuous at 0. In this case, you get f of 0, which is 0. So basically, from this, what is the sum from 1 to infinity minus 1 to the n over n squared? You move pi squared over 3, you divide by 4, you get negative pi squared over 12. Very nice, right? So this is a new technique, this is a new weapon that you add to your army that you can use to find the sum of an infinite series. If you remember in calculus 2, what techniques did you do to find the sum of infinite series? The first technique was telescoping sums, if you remember, then the geometric series, then the Maclaurin series. The Maclaurin series, yes, we used it to find certain sums that do not look very easy to find. And now we're using Maclaurin Taylor series, or sorry, we're using Fourier series now to find the sum of some interesting sums. You will see. This is the first example. Okay, now to better understand the idea, so remember, we started this example. This is the function. The first part of the question was to find the sum negative 1 to the n over n squared. We explained it in details. Now let's find, using the same data, the sum from 1 to infinity, not negative 1, sorry, 1 over n squared. So if you remember, 1 over n squared, the sum, this is called a p-series. This is, again, just a side to remind you. This was called p-series. What do we mean by the p-series? It's the sum 1 over n to the p, and to decide convergence, this is convergent only if p was bigger than 1, only. So in my case, the p is 2 because it's 1 over n squared, so we know from calculus 2 that it's convergent. But this is not what we want. What we want to find is the exact value of the sum. Again, convergent means that this sum, if you keep adding these terms up to infinity, you're getting a certain number. What is this number? This is what we want to find. This wasn't found in calculus 2. We didn't have enough techniques to find it. Now we can do it. So how do we do it? Again, I know that for the function x squared, of course, now I'm sure now you are wondering about, if we see the sum, how can we tell that we need to use the function x squared? Why don't we use the function x? Why don't we use the function x cubed? And so on. This is a valid question. At least for now, I'm telling you to use this function. In this example, I'm giving you the function x squared, okay? But in general, how do we find these sums? I will make a video about it, okay? But in general, so if you open the question, if you give me like an arbitrary series and you ask me find the sum, this is not an easy question, okay? So even the experts need time to find the appropriate function that produces the sum. In this example, I'm giving it to you, and this is what we need in this level of course, okay? but I will make one video to show you some hints, but they are of course very shallow, that can't help for very advanced sums. Now what happens usually when you get to the advanced level, what happens is that by reaching that level, you have seen already many examples with many cases, with many scenarios. So when you reach that level, once you see that sum, you say, okay, maybe if I use that idea from that example, I can get something. Then if you try it and it doesn't work, you say, okay, it doesn't work, but it's very close, so let me modify it by something. I will show you something like this, just very little later. Okay, so now we've seen that for the function x squared, the Fourier series is pi squared over 3 plus the sum from 1 to infinity minus 1 to the n multiplied with 4 over n squared cosine n x. We've seen this. So now again, the question is, you want to find the sum of 1 over n squared, right? The Fourier series has the sum. So now you ask, what's x? What's x that makes the summand 1 over n squared? So now you're looking for x that when you substitute into the cosine, what's inside the sum? The everything here becomes like 1 over n squared. So basically, because you're having minus 1 to the n inside the sum, it's like asking what value of x you substitute has the ability to cancel the negative 1 to the n. It's another negative 1 to the n, because if you have negative 1 to the n multiplied with negative 1 to the n, you get positive 1, right? So I think now the idea is very clear, and we need to substitute x as pi. Let's see why. So if you substitute x pi in the Fourier series, you get pi squared over 3 plus the sum. Now you will see again why pi. So you have cosine and pi. This is equal to what? F of pi from right, f of pi from left over 2. So pi squared over 3 plus 4 times the sum, negative 1 to the n over n squared. Now what's cosine and pi? It's negative 1 to the n, right? This quantity is exactly this. That's equal to, now what is f of pi from right from left? So we need to go back to the function x squared, the periodic function. This is very important. The periodic function x squared, and now you look at pi, so this is the pi, and you ask, if you approach it from left or from right, it's very clear that you're getting to the same point, pi squared. So you say, okay, this is pi squared plus pi squared over 2, which is just pi squared. So if you move the stuff, now negative 1 to the n here, negative 1 to the n, multiplied with negative 1 to the n, this is negative 1 squared to the n, which is positive 1. So this is when you get 1 over n squared. The right side is pi squared. We move the pi squared over 3 to the other side. So what's left is that the sum from 1 to infinity 1 over n squared, you divide by 4, you get pi squared over 6. This is a very interesting formula. If you add all squares of reciprocals, 1 over 1 square, 1 over 2 square, 1 over 3 square, if you keep adding all these numbers, you get pi squared over 6. I'm sure at the level of this course, this is the first time you see this sum. I'm sure you didn't see this sum in any of the previous calculus or the math courses in engineering, or even in math. I think this is the first time we see this sum. So this is the significance of Fourier. This is one application of Fourier series that you can apply to find some values that we can't find another way. Of course, the question now is Fourier series the only way, the only method we can use to find these sums? The answer is no, but this is one of the methods. At least at this level, maybe this is one of the easiest methods to find. Okay, so this is about the question. This is all about the question if the function is equal to the Fourier series or not. It is equal to the function if we have continuity, or the limit from right and from left over 2. Okay, this is the application. Another application, let's go back to the function f of x equal x. Of course, negative pi to pi, then extended periodically as usual. We've seen that the Fourier series is 2, that the sum from 1 to infinity, negative 1 to the n plus 1 over n sine nx, right? This is the Fourier series. So now what happens if we substitute, to show you how things work, what happens if we substitute pi over 2? What do we mean by substitute pi over 2? I mean, if you compute the Fourier series at pi over 2, this is going to be f of pi over 2 from right, f of pi over 2 from left over 2, right? So now if you substitute the pi over 2, you get 2 times the sum from 1 to infinity, negative 1 to the n plus 1 over n sine n pi over 2, right? Equals. Now what is f of pi over 2 from right, from left over 2? This is an easy thing because this is the function x from negative pi to pi. When you look at pi over 2, it's here in the middle, so the function is continuous, so you just substitute it and you get what? You get pi over 2, right? So this is the application of the Dirichlet test. But let's simplify this and see, let's see what this sum gives us, okay? Let's see what this sum gives us. So if you divide by the 2, you get n from 1 to infinity, negative 1 to the n plus 1 over n equals pi over 4, right? And here we have sine n pi over 2. Now, I want to show you this sine n pi over 2, what is it exactly, and then to see what this sum gives us. So the sum is from 1 to infinity. That means the n values are 1, 2, 3, up to infinity, right? So the n goes over all odd and even numbers. But if n was even, just look at this n. If this n was even, for example, if n was 2, the 2 is cancelled, you get sine pi, which is 0. If n was 4, you get sine 2 pi, which is 0. If n was 6, you get sine 3 pi, which is 0, right? So basically, when n is even, all these summands are zeros. That means when you take the sum, you don't need to add the even values. So that means, for example, if you're writing a code to compute this, and a loop to compute the sum like a loop, the loop step is 2, is not 1, right? So you start with 1, then you don't need to plug the 2, you substitute the 3. So I'm going to simplify this and to show you how to deal with these cases, because again, getting rid of these values, the even values, will simplify the form. We will see. So I think you all agree that in this sum, I don't need the even values. So okay, I'm adding the values from 1 to infinity, but only I'm looking at the odd numbers. I'm not looking at the even numbers, right? I'm sure most of us hate this form. We don't like seeing this form. And from 1 to infinity, and then you are saying n is odd. Let's simplify this a little. So the idea is, I want to write n from 1 to infinity. I'm not going to write n is odd, but I want somehow to impose that in my summand. So the idea is, if you replace n is going only over the odd numbers. So you need to replace the n by a general form that covers all odd numbers. But the general form that covers all odd numbers is 2n plus 1 or 2n minus 1. So which form do we take? 2n plus 1 or 2n minus 1? In this example, we should take 2n minus 1. And the reason is, if you take 2n plus 1 and you are writing n starts from 1, then 2n plus 1 starts from 3, but it should start from 1. That's why we should take it as 2n minus 1. And up, you must have minus 1. Again, you replace the n by 2n minus 1, right? Plus 1. Again, 2n minus 1, this is the replacement of n, but then you have another plus 1. This is an original plus 1. That's fine. Then you go back to, so you go to sine, the n, you replace it with 2n minus 1 pi over 2, right? All of this is equal to pi over 4. Let's simplify this a little. This is a very nice question. So this is minus 1. The minus 1 is cancelled here. And minus 1 to the 2n, this is positive 1, right? So we don't need to write it because it's negative 1 square to the n. So this is 1 over 2n minus 1, okay? Now what about this thing here? What about this thing here? Imagine n was 1. Just let's do the computations here, okay? I think we have enough space. So when n is 1, I'm computing sine 2n minus 1 over 2 pi, okay? So when n is 1, what do you get? You substitute 1, you get sine pi over 2, which is 1. When n is 2, you get sine 3 pi over 2, which is negative 1. When n is 3, you get sine 5 pi over 2, which is 1. When n is 4, you get what? You get negative 1, and so on. So it's very clear that this sign, it gives you negative 1 to a certain power all the time. When you have 1, negative 1, 1, negative 1, this alternating sign can be found using negative 1 to the power. But what power should we have? So when n is 1, you get 1. So if you write n, that's not true, because when n is 1, negative 1 to the 1 is negative. So we need to modify this. For example, we can change it to n plus 1. So when n is 1, you must get positive 1. And this is true because 1 plus 1 is 2, negative 1 squared is positive. When n is 2, 2 plus 1 is 3, negative 1 is 3 is negative. That's right. So you can check it, and yes, this is what we have. So this is equal to pi over 4. So if we just write this as negative 1 to the n plus 1, this is what you have. This is a very nice sum, right? So what this formula says is, if you add the alternating series, and at this stage, let me delete these computations here. So what this series is, so if you substitute the 1, what do you get? You get 1. If you substitute the 2, you get minus 1 over 3. Then plus 1 over 5. Then minus 1 over 7. Plus 1 over 9. And so on. All of this is pi over 4. So what you're saying is that the alternating series of the reciprocal of odd numbers with an alternating sign, the infinite sum is pi over 4. 1 minus 3rd plus 5th minus 7th plus 9th. In the end, you get pi over 4. This is a very nice example for an infinite sum. And at this point, I like to remind you that in the previous example, we found the alternating sum with n square, right? So minus 1 over n square, we found it like this, but using the function x square. So somehow, n square, we used the function x square. Here in this example, like we're dealing with n, just first power, we're taking the function x. So this is somehow a nice relation that we will emphasize more in next